Welcome back to the deep dive. Today, we are strapping in and talking about large language models, but specifically what happens after the fun part. What happens after you've fine-tuned one? The thing is, for you, the learner, this is all about accessibility now. I mean, techniques like QLoRA let you fine-tune these huge models on pretty modest hardware. It's fast, it's cheap, but that's the central trap we're diving into. A model that successfully finished training is absolutely not the same thing as a model that's ready for production.
Exactly. Teams get these fantastic training results, they get excited, and they rush to deploy.
And then what happens?
A few weeks later, they find out the model is subtly drifting, or it's starting to generate these really confident hallucinations, or maybe it's just, silently getting slower under real user load.
And trust is lost. Money is lost. So that gap, the one between a successful training run and a safe shipment, that is the mission of this deep dive. We're going to give you a practical, repeatable workflow to test the model and the whole infrastructure around it before you push that big red launch button.
And we're aiming for confidence here, right? Not some kind of unattainable perfection.
Exactly. Confidence.
But ground this, let's use a mental model from the sources, the one about the high-performance race car. I think it works really well.
Okay.
So fine-tuning, that's like swapping the engine, tuning it on a dyno for maximum horsepower. It's a controlled environment.
Right. It tells you what the engine can do, in theory.
In theory. But testing is everything else that happens before the car ever hits the track.
It's checking the brakes, how the suspension reacts on a rough corner, what happens when the fuel tank is half empty, all that stuff.
It's preventing you from discovering a critical brake problem when you're already going 120 miles per hour.
Yeah.
And the real challenge here is that traditional, deterministic software QA, it fails immediately.
Because you can't just run the same test 10 times and expect the same output.
Not a chance.
So, if the output isn't deterministic, what are the new questions we have to start asking? The things a normal QA engineer might just ignore.
We have to shift our focus. It's less about, is the answer right? And more about, is it reliable and is it useful?
Okay.
So we need to know, does it actually perform the task better than the base model did? Is the output quality good, or is it just, fluent but confidently wrong?
I hate those.
We all do. And then you hit the operational questions. Latency specifically, time to first token, or TTFT.
That's that critical delay before the user sees the first word pop up.
Exactly. And we have to check environment parity. Does it work the same in a Docker container as it did on your test GPU? And what's the peak VRAM usage?
VRAM, the video RAM on the GPU, that's so critical. If you run out of that, your model either crashes or it just grinds to a halt.
It grinds to a halt. And this gets even more complex with, say, multimodal language models, MLLMs. They're basically coupled engines.
A vision encoder and a text decoder.
Right. And a model can pass all its text-only latency tests perfectly. But then a user uploads a high-res image, and suddenly the vision pre-processing takes forever, and it just dominates that critical TTFT metric.
So you get these massive, unexpected latency jumps in production.
If you don't test those modalities separately, you will.
Which highlights the need for some kind of foundational rule. If we can't rely on deterministic outcomes, we need a core principle to anchor all of this.
And that principle has to be absolute reproducibility. The golden rule is just this simple. If it isn't logged, it didn't happen.
I like that.
Because if a user reports a model failure, and you can't just hit a button and instantly rerun that exact scenario under those exact conditions, you can't debug it. It's just guesswork.
Okay, so for a small team, they're trying to keep overhead low. What is the absolute bare minimum data they have to log for every single inference run?
Okay, you need the input prompts and the full complete model outputs. And crucially, you need to freeze a golden prompt set, a stable, never-changing set of prompts.
For your core tasks and known failure modes.
Exactly. Then, the specific model version and checkpoint. You have to log the exact inference configurations of temperature, top app, all that. And finally, the hardware context is non-negotiable. GBazoo model, CUDA version, and those basic performance metrics we talked about. TTFT, tokens per second, and peak VRAM.
That audit trail is what turns this from guesswork into engineering.
That's the whole game.
Okay, that's the infrastructure. Let's get into the process itself. You suggested organizing this whole thing into 6 distinct testing lanes. I love the race car analogy for this, too.
It just fits so well. Think of it like this. Lanes 1 through 4 are all about validating a single car. Is it engineered well? Is it sound?
Okay.
Lane 5 is where you choose which car to actually race. That's the comparative stage. And lane 6, that's where you decide if the car is safe enough to hand the keys to someone else. Trustworthiness.
All right, let's unpack this. Lane 1.
Lane 1, functional testing. This is the most fundamental question. Does the fine-tuned model actually do the primary job it was trained for? And is it better than the base model?
What does a proper test run for that look like? I'm guessing it's more than just one or two
Oh,
checks.
absolutely. You're running maybe 20 to 50 task representative prompts from that frozen golden set we mentioned. Plus, and this is important, you need messy, real-world examples.
What do you mean by messy?
Things like misspelled inputs, prompts with extra irrelevant paragraphs, or instructions that are buried in the middle of the text instead of at the start.
And what's a pass here? Is it 100%?
Nah, perfection is pretty much unattainable. We look for something like 90% or more acceptable outputs on a human review, but the red flags here can be really subtle.
Okay.
The big one is confident hallucination, obviously, but a quieter one is a shift in tone or verbosity. Say you fine-tuned it to be concise, but now it's giving you these long, rambling, overly polite answers. Even if they're technically accurate, that's a functional failure.
Because it's drifted from its intended personality.
Exactly.
Yeah.
So that's lane one. Now, lane two shifts our focus from what we gained to, well, to what we might have lost.
Lane 2, regression testing.
The goal here is, what did we break? We're laser-focused on something called catastrophic forgetting.
So, like, we fine-tuned it so intensely on medical data that it forgot how to do basic math or translate Spanish.
That is precisely it. The test run here uses a stable set of general prompts that test things outside the fine-tuned domain. So math, general knowledge, simple reasoning. And crucially, you have to compare the fine-tuned model against the original base model, not just your last checkpoint.
What does a catastrophic failure look like in practice here?
Well, the obvious one is a major drop in reasoning scores. But a more insidious red flag is when the model tries to force everything into its new specialty.
Give me an example.
Imagine you fine-tuned it to be a real estate assistant. You ask it, what is the capital of Japan? And it replies with, while I cannot answer general knowledge questions, I advise you consult a licensed agent regarding commercial investment in Asian markets.
Ah, so it's developed this tunnel vision that breaks its core utility.
That's the failure mode. That's a huge red flag.
That's a great example. Okay, let's talk about the speed limit. Lane 3 is performance testing.
Right. Quality is totally irrelevant if the model is too slow or too expensive to run. The goal of lane 3 is, can we actually ship this thing at scale?
So we're back to measuring those key metrics: TTFT, tokens per second, P95 latency, and peak VRAM. Can you define P95 for us?
P95, or the 95th percentile latency, just means that 95% of your users will get a response that's equal to or faster than that number. We don't use the average because an average can hide the fact that, say, 5% of your users are having a horrible, painfully slow experience. P95 captures the experience for the vast majority.
And the pass criteria here.
Your TTFT has to be within your UX budget, usually under a second or two, and you need critical VRAM headroom. Maybe 15 to 20%. If your VRAM usage is at 98%, your server is basically one concurrent user away from crashing.
What are the weird hidden red flags in performance testing?
Latency clips. You're testing with 500 token prompts and it's super fast. But the moment you hit 1,500 tokens, the latency just spikes because of how it's managing its cache.
Oh, wow.
Also, watch out for throughput degrading over time. That can signal a memory leak that only shows up after thousands of requests. And of course, the classic out-of-memory errors that only appear when it's containerized in Docker.
Ugh, environment parity. It always gets you.
Always.
Okay, lane 4. This is where we deliberately try to crash the car. Stress and edge case testing.
The goal isn't to be comprehensive. It's to understand how the model degrades. We want to see how it behaves when we push it past its limits.
So we're feeding it adversarial inputs.
Yep, empty prompts, inputs to the absolute maximum context length, really ambiguous instructions, prompt injection attempts, jailbreaks, you name it.
So we're not trying to patch every single hole, but just making sure it fails safely and predictably.
Exactly.
Oh.
The model passes if its degradation is graceful, if its refusals are consistent, the red flags are catastrophic. Just nonsensical gibberish near the max context, crashing or hanging on weird inputs, or, any safety bypasses.
And if your team finds a failure mode but can't replicate it,
You go back to the logging rules. It means you weren't saving the inference context that caused the crash in the first place.
got it. Okay, lane 5, comparative testing. We've validated a single model. Now we have to force some explicit trade-offs.
It seems good is not a shipping criterion. You have to be able to answer, is this version actually better than the last one? So you run identical prompt sets with identical parameters across different models.
So base versus fine-tuned.
Earlier checkpoint versus a later one. And critically, the quantized version versus the full precision version.
Why is this so necessary if we already did functional testing in lane 1?
Because L1 just tells you if it works.
Yeah.
L5 tells you if the engineering effort was worth it. We need documented trade-offs. You pass if there's clear, measurable improvement on your target tasks. A huge red flag is if your later checkpoints start performing worse.
Which would point to problems in your training data or process.
Usually, yeah, instabilities.
Okay, and finally, lane 6. Quality evaluation. This hits the hardest question. Would a human actually trust this?
And this is necessary because all those automated metrics like Rouge or BLEU scores, they're just proxies for quality. They aren't enough on their own. We have to evaluate the subjective human experience.
How do you operationalize something as fuzzy as human trust?
You take a sample of, say, 20 to 50 outputs, and you have people score them using a structured rubric.
A rubric that evaluates what?
Factual accuracy, tone, safety, completeness, and this is a big one, consistency. If you don't have the people for that, a strong LLM as judge setup can work, but you have to validate that first.
What's a failure state in quality evaluation?
You pass if your hallucination rate is below a predefined threshold. Maybe less than 2% of answers have factual errors. And if your scores are high with low variance, the absolute worst red flag is the confidently wrong, highly fluent answer.
Because a simple mistake is just annoying.
But a confident lie, delivered in perfect prose, is destructive to user trust. It's so much harder for a user to spot. Lane 6 is designed to filter that out.
Okay, let's zoom out a bit. You mentioned that reasoning ability often causes failures because people treat it as this separate thing to check off a list.
It's not a silo. It's a cross-lane reality. And if you only check it once, you assume it's covered everywhere, and that is how subtle failures slip into production.
So you're checking it at every stage.
You have to. You check it in lane 1. Does it support the task? You check it in lane 2. Did we degrade general reasoning? You check it in lane 5. Which model variant reasons better? And in lane 6, would a human actually trust the explanation the model gives?
Which brings us to the famous standardized benchmarks, like MMLU or GSM-8K. Everyone loves posting their high scores, but our sources stress they are not guarantees of production readiness.
Not at all. They're powerful tools, but they answer the question, did something change? Not, does this matter to my users?
So where do they fit in?
They're best used as regression tripwires in lane 2 and as tiebreakers in lane 5.
Can you break that down? Which benchmarks for which role?
Sure. MMLU or HelloSwag, those are great for checking general capability health. If those scores drop, you know you have catastrophic forgetting. GSM-8K or RAC challenge are good for reasoning stability. Truthful QA is for, well, truthfulness.
But a high score on GSM-8K doesn't mean it's going to be correct on my specific domain tasks.
Absolutely not. Doesn't guarantee correctness on calculating legal risk or financial forecasts. Not even close.
Okay, another big operational reality is quantization, moving to 4-bit or 8-bit for speed.
And we have to emphasize this. If you quantize your model, you have created a new model. You cannot assume it behaves the same.
You might save 50% on VRAM.
But you might have introduced noise or reduced its ability to follow complex instructions. So you have to rerun lane 1 for quality loss, lane 3 to verify the performance gains, and lane 5 to document that trade-off explicitly.
Okay, I can see how seeing all 6 lanes and the logging requirements might feel a little overwhelming, especially for a small team.
For sure. And we can't let the perfect be the enemy of the good, or in this case, the ship.
So you bring in this concept of the trust budget.
Exactly. Your testing effort has to be balanced against your time-to-market pressure versus your trust budget, which is just how much room you have to be wrong in production.
Can you give us some contrasting examples?
Sure. If you're building a creative writing assistant for internal brainstorming, your trust budget is high. Failure is just annoying, not fatal.
Right.
But if you're building a medical summarizer for patient records or a legal contract drafter, failure could mean losing a client, creating liability, causing real harm. That is a very, very low trust budget.
And the effort you put into lane 6, the quality evaluation, has to scale with that budget.
Dramatically.
And this budget also kind of dictates which lanes a team prioritizes based on how mature they are.
Right. The hair on fire startup, they just need to prove their feature is cool. So they focus on lane 1, does it work? And lane 4, will it crash our server?
They can skip the rest for now.
For now. Then you have the growth stage company. Now user churn and costs matter. They need to add lane 2, regression, to do no harm, and lane 3, performance, because latency matters at scale.
And then the high-stakes enterprise.
That's where the trust budget is razor thin. They need the full 6-lane suite. For them, lane 5 and lane 6 become the primary gates for any release.
And if you find yourself just paralyzed by this whole list, you have a simple ship it heuristic.
Just ask yourself one simple, practical question. If this model fails in a way I didn't test for, will I lose a user forever, or will I just get a support ticket?
If it's just a support ticket, ship it.
Ship it. You can build out the rest of the testing harness later. In fact, you should use those support tickets, those real-world failures, to define your next golden prompts for lane 1 and lane 4.
And the tooling philosophy follows from that.
It does. Tools are force multipliers. Use LME harness for your regression tripwires in L2. Use something like PromFu to lock down your golden prompts in L1. Choose tools to strengthen the lane you're focused on.
The ultimate goal is turning that intuition into repeatable, auditable engineering.
That's it. This whole process is what transforms fine-tuning from a risky experiment into a defensible engineering practice.
So when we define ready to ship, we're really talking about reducing uncertainty in a way that's explainable and reproducible. It means you can point to evidence.
Evidence that says functional tests pass, no major regressions, performance meets targets with VRAM headroom, edge cases fail safely.
And most importantly, all your test artifacts are saved, all those logged outputs and metrics.
Because if you can explain, with evidence, what your model is good at, where it predictably fails, how it behaves under load, and why you chose this version over all the others, you are operating, not guessing. Future, you won't care how clever the fine-tuning was. They will only care that you can explain in minutes what went wrong and what needs to happen next.
A perfect way to frame the engineering discipline of LLMs.
So let's leave you with a provocative thought that builds on what we just discussed, especially around long context testing. Synthetic tests like needle in a haystack are great for verifying that the context window works mechanically. The model can find a buried fact, but that doesn't prove it truly understands long context.
Right.
So if you achieved high scores on a test like that, what unseen scenario 1 involving subtle, contradictory facts buried deep in a 20,000 token prompt? What scenario might still lead to a highly confident hallucination? And since you can't wait for your users to discover it, how would you build a novel test for that specific failure mode today, given your current trust budget? Something to think about as you get ready for your next deployment.